Okay, so welcome back, and now in this video I'm going to introduce two more common polar curves that we're going to run into quite frequently, and we're going to study more of these and how they behave and how to understand the characteristics. So this one is called a Lemasana. That's the way it's pronounced. It's Lemasana. And a Lemasana is very similar to cardioid. In fact, a cardioid is just a special case of a Lemasana, where A is equal to B or A is equal to negative B, okay? So in this case, you'll notice that it's very similar to the equation that we saw with a cardioid, okay? So a Lemasana will either be of the form R equals A times cosine theta plus B, or A sine theta plus B, okay? And again, A and B are arbitrary constants. And so it's going to have some shape like this, okay? Now, then there's the rose, okay? Now the rose has petals. Very interesting thing about the petals, as you're going to see in a moment. So a rose has these type of functions here. Either A equals A cosine times B times theta. So, excuse me, let me rephrase it. A times cosine of B times theta. So some multiple of theta is the angle, okay? Or a sine of a multiple of theta. Okay, so now either one of these will give us what we call a rose. Now let's look at the examples here. So here we've got R equals 3 times sine 2 theta. Now notice how many petals there are. There are 4 petals here. But if you take R3 sine 3 theta, then you only have 3 petals. So one of the interesting things to note is that if the multiple of theta, if the coefficient of theta is even, we get double the number of petals. So this is 2, we end up with 4 petals. If the coefficient on theta is odd, we end up getting the number of petals equal to the coefficient, which in this case is 3, okay? So it's good, and it's actually worth investigating these things more, okay? When we start talking about graphing these things, right? So if we can understand the behavior when we look at the different pieces or parts of the function or the equation, then we can understand how these things are going to look and be able to sketch the graph of these easier. Okay, so now again, you're encouraged to investigate, explore. Why is this the way it is? Why does it, when it's even, we get an even number or double the number of petals, but when it's odd, we get the same number of petals as the coefficient, okay? So I encourage you, investigate that, okay? Explore why that happens. Now, even more interesting graphs emerge when the coefficient of theta is not an integer, okay? So far we've dealt with integer coefficients. So for example, if the coefficient is rational, we've talked about this a little bit before. If the coefficient is rational, we get a pattern that repeats itself. Okay? So which means that the curve will eventually end where it started. So if it's rational, we get what we call a closed curve. Okay? But if the coefficient is irrational, like the square root of 2 or the square root of 3 or the square root of 5, then the curve never closes. And what will eventually end, it becomes a space-filling curve. Okay? Now, although it may appear that the curve is closed, a closer examination will reveal that the petals just above the positive x-axis are slightly thicker. Okay? And this is because the petal does not quite match up with the starting point. Okay, so if you're able to zoom in, you would see that. Okay, so here's some examples of what I'm talking about. Okay, so here's, again, we've seen these before. Okay. So this one here is a closed pattern. Okay, it's a closed curve. This one over here is not. And this one here is what we call a space filling curve because it fills in. It's going to start filling in the space the more it keeps going. Okay? So that's other things to keep in mind. What else can I say about this? Oh, another irrational coefficient would be pi, right? Pi is a common one. Let's see. Okay, I think that's all I want to do now. Okay, we'll leave it at that, and next time we'll start getting into more spirals and other, going into some of these curves in more detail and plotting them and seeing what kind of behaviors they have. See you then.